We're going to be looking at enthalpy, which is a state function. A state function is a function that does not depend on how the state is reached. It only depends on what state the system is in. An example is climbing a mountain. You can climb it straight from bottom to top, or you can take a more circuitous route that's a bit less steep, but you have to walk a longer distance to get there. In the end, you still reach the same elevation or altitude. The difference between the summit and the base is still the same. Enthalpy is an example of a state function and is represented with a capital H. Our official definition of enthalpy is an equation. H equals U, the system's internal energy, plus PV, where P is pressure and the V is volume. The equation for change in enthalpy has some deltas to represent change. Delta H, change in enthalpy, equals delta U, change in internal energy, plus pressure times the change in volume, P times delta V. I'm not going to bore you with the proof equations, but we could take that change in enthalpy equation and turn it into a more useful one. Delta H, change in enthalpy, equals Q sub P, heat at constant pressure. That means heat and enthalpy are interchangeable as long as the process is happening at constant pressure. Because of this, I may sometimes refer to enthalpy as heat. It's commonly done since enthalpy is represented with an H, and they're basically interchangeable. We need to follow some rules for using delta H. First, values for delta H are tied to the coefficients in the chemical equation that the delta H is associated with. If the coefficients, which can represent number of moles, change, the delta H must also change. Let's say we multiply our coefficients by some value. We must also multiply the delta H by that same value. For example, if we multiply the coefficients by 2, we must multiply our delta H by 2. If we divide our coefficients by 2, we'll divide our delta H by 2. This is because delta H is an extensive property. Remember, extensive properties depend on the amount of matter present. 4 moles would be associated with a different amount of energy compared to 2 moles. The enthalpy change, delta H, is going to depend on the physical state of reactants and products. Whether it's a solid, liquid, gas, or aqueous solution is going to affect the values that we're plugging into our calculations. Knowing the states of matter is going to be really important in this chapter for looking up correct values in tables. Remember, delta H and Q are basically interchangeable. Just like with Q, if we get a negative value of delta H, the reaction is exothermic. And if we get a positive value of delta H, the reaction is endothermic. Our last rule is that if you reverse an equation, that is, if you put the products on the reactant side and the reactants on the product side, then the sign on the delta H needs to be reversed. If delta H for the forward reaction is positive, the delta H for the reverse reaction is negative, and vice versa. Here's an example of a calculation we can do to find enthalpy change. We have an equation given to us in the problem of hydrochloric acid reacting with sodium hydroxide to make sodium chloride and water. We're told that when 0.05 moles of HCl reacts with 0.05 moles of sodium hydroxide to form 0.05 moles of sodium chloride, then 2.9 kilojoules of heat are produced. We want to find the enthalpy per mole of acid that reacts. Since our balanced chemical equation has coefficients of 1 in front of each thing, the equation the way it's written is 1 mole of HCl reacts with 1 mole of sodium hydroxide to make 1 mole of sodium chloride and 1 mole of water. We want to find how many kilojoules would be associated with the reaction as written, since the reaction as written involves 1 mole of hydrochloric acid, and we want to find enthalpy per mole of acid that reacts. However, when the reaction was done in the lab, it was with a different number of moles, 0.05 moles of each thing in the reaction, and 2.9 kilojoules were produced. It may be helpful to rewrite our equation with coefficients of 0.05 and write the 2.9 kilojoules next to the equation that it's associated with. Remember, the coefficients and the delta H are linked. Change one and you have to change the other. This is basically a stoichiometry problem. but you can use enthalpy in the conversion factor in the same way you would a coefficient from the equation. You just have to make sure that you are using enthalpies and coefficients that actually correspond to each other. The 2.9 kilojoules doesn't correspond to 1 mole of HCl. It corresponds to 0.05 moles of HCl. We're trying to find the amount of heat that corresponds to 1 mole of hydrochloric acid. So first we start with 1 mole of HCl as our initial value, and then we'll use the known relationship between moles of acid and kilojoules of heat as a conversion factor. In our conversion factor, we want moles of HCl on the bottom to cancel out, and kilojoules on the top since we're trying to find the enthalpy, the delta H, per mole of acid. We do 1 times 2.9 divided by 0.05, and that gives us 58 kilojoules associated with 1 mole of acid. What mass of iron must be in a hot pack to provide negative 335 kilojoules of heat when the iron reacts with oxygen and is converted to iron 3 oxide according to the following thermochemical equation? 2 iron solid reacts with 1.5 oxygen, O2 gas, to make iron 3 oxide, Fe2O3 solid. The associated delta H is negative 824.2 kilojoules. This problem is very similar to the previous one in that you can use a known relationship between a delta H and a coefficient from a chemical equation in order to solve for something that's unknown. In this case, we have a balanced chemical equation given to us and a delta H associated with that balanced chemical equation. When we have 2 moles of iron, negative 824.2 kilojoules of heat would be produced. And the question is, what mass of iron would be needed to make negative 335 kilojoules of heat? Notice it's asking for mass of iron, so all your answers are in grams, but our relationship is between kilojoules and moles. Is the answer A, 45.4 grams, B, 22.7 grams, C, 89.2 grams, or D, 90.8 grams? The correct answer is A, 45.4 grams. You're going to take your negative 335 joules as your starting value and use a conversion factor between heat and moles. Our conversion factor is that for every 2 moles of iron, negative 824.2 kilojoules of heat are produced. That would give us our number of moles of iron that would be needed. Then we can take those moles and convert them into grams using the molar mass of iron. We can do enthalpy stoichiometry calculations with limiting reactants. Anytime that you're given 2 different starting masses, the masses of 2 different reactants, it will be a limiting reactant problem, whether it says so or not. In this problem, 2.67 grams of sucrose react with 7.19 grams of potassium chlorate. That doesn't necessarily mean that all of the sucrose or all of the potassium chlorate will get used up. First, we're going to have to find which is the limiting reactant. We're told when that reaction with those starting amounts happens, 43.7 kilojoules of heat are produced. We are asked to find the enthalpy change for the reaction. What's implied by that is we want to find it for the reaction in our equation as written. That is, when we have 1 mole of the sucrose reacting with 8 moles of potassium chlorate to make 12 moles of CO2, 11 moles of water, and 8 moles of potassium chloride. The first thing we're going to have to do is go from grams of sucrose to moles of sucrose by dividing by the molar mass of sucrose. Notice that grams cancels out with grams, and molar mass always goes next to grams. So that gives us 0.00780 moles of sucrose. Then we can go from moles of sucrose to moles of one of the products. We'll arbitrarily choose CO2. To find moles of CO2, we use a stoichiometric factor based on our balanced chemical equation. There's a 12 next to the CO2, and there's an understood 1 next to the sucrose. We're multiplying by 12, and that gives us 0.0936 moles of CO2. Now we're going to do the same type of calculation, but with our other reactant, the potassium chlorate. We go from grams of potassium chlorate to moles of potassium chlorate. We take our 7.19 grams of potassium chlorate, divide by the molar mass of potassium chlorate, which is 122.5. Again, grams cancels out with grams, and molar mass is on the bottom next to grams. We come out with 0.05869 moles of potassium chlorate. Then we go from moles of potassium chlorate to moles of the same product as before, the CO2, using a stoichiometric factor. We have a 12 in our equation next to the CO2 and an 8 next to the potassium chlorate. Notice the moles of potassium chlorate are canceling out with each other, and we end up with 0.0880 moles of CO2. The other starting material, the sucrose, could yield 0.0936 moles of CO2 if it reacted fully. So the value based on the potassium chlorate, 0.0880, is the smaller of the two values, which means the potassium chlorate is the limiting reactant. Now that we know the limiting reactant, we can use the relationship between moles of potassium chlorate that reacted and heat that was produced as a conversion factor. So we can find how much heat would be produced with 8 moles of potassium chlorate. We start with 8 moles of potassium chlorate. We have moles of potassium chlorate on the bottom, filled in with the moles we calculated at the top of the slide, 0.05869. We have 43.7, the corresponding enthalpy, on the top. We do 8 times 43.7 divided by 0.05869, and that gives us 5,957 kilojoules for the original balanced equation.